Hello guys, in this video I would like to discuss about acid, base and salt preparation. So acid is a compound that contains hydrogen, or actually it acts as hydrogen or proton donor. It means that it can have the ability to give out hydrogen to other compound. While base actually is a hydrogen or proton acceptor, and usually it neutralizes acid. So example for acid, they usually have hydrogen atoms in their molecule. For example, like hydrochloric acid and then nitric acid. So the naming should be blah 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 acid, sulfuric acid and so on. And if you see that most of them contains hydrogen plus. For example, like hydrochloric acid. So hydrochloric acid, the shape is should be like this. It is a 1 hydrogen plus ion and then 1 Cl minus ion. You can know this positive and negative charge from the ionic chart. It can also have 2 hydrogen ions, for example like sulfuric acid. Sulfuric acid has 2 hydrogen ions because actually, if you know, this is hydrogen. They are bound to sulfate, SO4, 2 minus. Therefore, we need 2 hydrogens in order to balance the charge. So H2SO4 in this case. But the name is just sulfuric acid. So there are some important acids that you must remember for IGCSE, which are hydrochloric acid, nitric acid, and sulfuric acid. These 3. While for base, they usually act as hydrogen or proton acceptor, and they contain what is called by the hydroxide ion. Typically, hydroxide ion can be bound to any metals or any positive charged ions. For example, like I have sodium hydroxide. Well, sodium is +1, so I have this one thing, and then hydroxide is OH -1. So the formula will be NaOH. I also have, like, let's say, calcium hydroxide. So this is calcium +2, hydroxide should be like this. Therefore, the formula for calcium hydroxide will be CaOH 2 times, because we need 2 hydroxide ions in order to balance the charge from the calcium. So CaOH2. Typically, this is some of the few simple examples of base that you will find in IGCSE. They would always contain OH -1 ion, so NaOH. And if you see that all of these actually they are formed through ionic bonds usually. So if you submerge them in water, they will usually be dissociated or ionized. Acid must always be soluble in water. So acid must always be soluble in water. While for base, it depends. Now, before we speak about the ionization, I would like to speak about the strength of an acid or base. The strength of an acid and base is mentioned or discussed in the scale of pH. So this is called the pH scale. And what we have here is the universal indicator. So the universal indicator actually gives out color depending on the pH of an acid or base. So what is a pH? So a pH is an abbreviation called the potential of hydrogen. So it means it gives out the strength of an acid typically. So the lower the pH is, the more acidic it is, while the higher the pH is, well, it becomes more basic. Neutral should be 7, exactly in the middle. And in universal indicator, actually they are colored so that it's easy for us to identify the strength of an acid or base. So let's say that you found an unknown sample and then you put in universal indicator, and then the universal indicator will change color and tell us about the strength of that acid and base. So this kind of important. For example, you found like a red substance after being submerged to universal indicator. It means that it's very acidic. For example, like stomach acid. While for Coca-Cola, I think it's like 4 or 5. So it should be orange instead of red. For your soap, should be purple, something like that. So this is the universal indicator. Aside from universal indicator, we also have some indicators that can also change color depending on the pH scale. For example, one famous example is called phenolphthalein. Phenolphthalein, which would change color from colorless to pink. So while it's still acid, it will be colorless. When it's pink, it will be base. Also some simple indicator, for example, like litmus paper. Because litmus paper actually also changes color depending on the pH of the solution. For example, like if your solution is acid, then the litmus paper will change into red. And if your solution is base, the litmus paper will change into blue. And there are actually many more indicators that can be used in nature. But here are some of the more common examples. Okay, so now we've discussed the potential of hydrogen or the pH scale. Now I would like to speak about the distinction between strong and weak acid or base. So what defines strong and weak? Well, yeah, indeed that the pH would have something to say about the strength of an acid or base. However, the characteristics of strong or weak acid and base, it actually depends on the dissociation potential. So for example, like you have hydrochloric acid. Typically, the whole molecule would look like this. And then you submerge it in water. Because hydrochloric acid is soluble. So water is able to break this ionic bond between them actually. Now, if it is broken, it will form hydrogen plus and Cl minus ion freely roaming inside the solution. So the hydrogen and the Cl minus ion will be swimming freely. If it is a strong acid, then all of your molecule, so all of your molecule, 100% of your molecule will change into their ion form. While for a weak acid, for example, like an organic acid, let's say we have acetic acid, so CH3COOH or vinegar, yeah, their formula is actually H plus and CH3COO minus. Well, some of them would actually dissociate. So some of them would create these ions, some. But many of them, so predominantly, they will stay in their whole form. They will stay. But if we see and evaluate, actually pH is the potential of hydrogen. So if the hydrogen that is released is less, then that explains why acetic acid or vinegar would be considered as a weak acid compared to hydrochloric acid. So hydrochloric acid is able to release all of its hydrogen atoms, while for acetic acid or vinegar, only partially can be released in the solution. So usually strong acid are mineral acid, or inorganic acid. Yeah, for example, like hydrochloric acid, hydroiodic acid, and then nitric acid, sulfuric acid, and so on. While for weak acid, they are mostly organic acid like citric acid, then vinegar, and then lactic acid, for example, from milk, and so on. For base also, it works the same way, that we have strong and weak base. For strong base, they will dissociate completely, dissociates perfectly into hydroxide ions and their metal, while for weak base, mostly they will remain in the whole molecule form instead of being dissociated. So this is actually the distinction between strong and weak acid. Now I want to speak about the reactions. So acid and base can actually react. And if acid and base react, they will form a salt. They will form a salt also by releasing water molecule. This is the first type of reaction. So salt is not limited to just table salt. Yeah, sometimes people they try to direct their thoughts. Yeah, if they hear about salt, then they think about that one salt in your kitchen. But that's not always the case. But salt is actually a category of compound that is formed from a reaction between acid and base. Now let me give you an example of an acid. Let's say nitric acid, and then a base, let's say sodium hydroxide. Then what would be the salt form? So the salt that is formed, it's always depends on the metal of the base. So sodium, the metal of the base, and this part of the acid. Yeah. So the negative part of the acid, the negatively charged ion part of the acid. So the nitric. So it should be sodium nitrate, right? No. When we call it salt, the nitric part change into nitrate. So the name should be sodium nitrate. And water. So if you have hydrochloric acid, then you would make chloride salt. If you have nitric acid, you would make nitrate salt. If you have sulfuric acid, then you will make sulfate salt. So the name of the salt also depends on the acid, and the metal part depends on the base. And how to write this in simple formula, then you have to refer to the ionic charge. Sodium is +1, nitrate is -1, so sodium nitrate is NaNO3. So this is the first type of reaction. Second type of reaction would be acid and metal. They will form actually the same, so salt, but hydrogen gas instead of water. Yeah. Technically the same concept, that the metal part will be the metal part of the salt. For example, I have sulfuric acid, and then I have, let's say, potassium. Then I would have potassium sulfate and hydrogen. Yeah, because potassium is the metal part, and then sulfuric, yeah, I take the negative part from the acid. Now for the third reaction, actually, it's acid and metal carbonate. It will form salt also, but it will form water and carbon dioxide gas. So for the acid, let's give an example. It's hydrochloric acid. And the metal carbonate, let's say calcium carbonate. So technically it's the same. We take the metal part from the metal, take the metal part, and then take the negative part from the acid. Therefore we have calcium chloride and water and carbon dioxide. So in order to make the salt, always take the metal part and then the negative ion part from the acid. And the negative ion part from the acid will always be like this: hydrochloric acid, chloride, nitrate, and sulfate. I think these three are the most common ones. Before I speak about solubility rules, I would like to discuss about oxides. It cannot, okay. Let's discuss here first. So I want to discuss about oxide because oxide is kind of important. So oxides, actually they are a compound, yeah, that contain oxygen and other atoms. Yeah, I would differentiate them into two different types. So there are metal oxides and there are non-metal oxides. So metal oxides, technically it's a metal bound to oxygen. They form a molecule. Well, for non-metal oxides, yeah, non-metal things, then they're bound to oxygen, then they create a molecule. Example for metal oxide can be calcium oxide, then magnesium oxide, and many more. While for non-metal oxide, yeah, non-metal, so for example like carbon dioxide or sulfur trioxide or nitrogen dioxide, and many more. So you see that this part, they are non-metals, while this part, they are metals. Metal oxide, typically they are not soluble, so they remain solid, yeah guys. In solution, they remain solid, while for non-metal oxides, typically they are in the form of gas. If you submerge them or react them, calcium oxide oftentimes can react with acid. So this thing can react with acid. It means that they are a bit basic, so their characteristics is a bit basic, because in water they will actually release hydroxide ions. So metal oxides can react with acid, while for non-metal oxide usually they can react with base. Okay, this is just for your information. However, we do have like special oxide. It's called amphoteric oxide. Yeah, which we have two actually. So aluminum oxide and zinc oxide. Being amphoteric means that they can react with both acid and base. Yeah, so they're kind of versatile and flexible, can react with any of these. Okay, so these are oxides, and I hope you also know how to write the state of matter for these compounds. Finally, as the final part of this chapter, you also need to learn how to prepare a salt. So that is why here I put general solubility rules first, in order to teach you how to notate a salt, whether it's aqueous or solid. So soluble salts, it means that they are soluble in water. It means that if you put in water, they will become aqueous solution. While for insoluble salts, it means that if you put them in water, then there's no point, because they will just form a sediment or precipitate. So how can we identify? Here we see that soluble salts, all sodium, potassium, and ammonium salt. So actually, if you find sodium with anything, sodium chloride, sodium nitrate, sodium sulfate, or also potassium, they will also be soluble or aqueous. While for nitrate, so for example like magnesium nitrate, calcium nitrate, whatever, with nitrate, they should be soluble. So it's quite easy to memorize these two, because everything with them will just be soluble. While for chlorides, typically they are soluble, with the exception of silver and lead chloride. So if you have silver chloride or lead chloride, it means that they are insoluble. Other than that, yeah, they are soluble. For sulfate, they are also usually soluble, except for barium, lead, and calcium sulfate. So barium sulfate is not soluble, lead sulfate and calcium sulfate is also not soluble. For insoluble salts, they are carbonates. So if you see carbonates, they are usually insoluble, except if you pair them with potassium, sodium, and ammonium, which has a high solubility capability. While for hydroxides, this is actually base. So almost all bases are insoluble, except, well, sodium, potassium, and ammonium hydroxide. For IGCSE, I think this information should be enough. So if you have sodium hydroxide, potassium hydroxide, and ammonium hydroxide, then they would be soluble. Other than that, it should be insoluble. For all acid, they are soluble. So all acids are here. So when you want to prepare a salt, there are some general consideration that you have to think first. So first you have to ask whether your salt is soluble or not. This is the first question. So there can be two answers. Yes, your salt is soluble, and no, your salt is not soluble. Okay. Now, if your salt is soluble, then we have also another question. Are your materials soluble? Yeah, also two possibility, yes and no. If your materials are soluble, then it means that you're doing titration. If your materials are not soluble, it means that you're doing excess solid method. And if your salt is insoluble, you're only doing one method, which is precipitation. Now, let us discuss about creating insoluble salt first. Let's say that I want to prepare barium sulfate salt. So I want to make this. Before I even prepare anything, before I prepare the solution, I prepare the materials, or I even touch the glassware, I need to check whether barium sulfate is soluble or insoluble. So let's see this chart. Sulfate. Sulfate is here, and barium sulfate is actually insoluble. So barium sulfate should be solid. It means that from this flow chart, is your salt soluble? No. So we should use precipitation method. So now let's think about some possible materials for us to get barium sulfate. So as we discussed before, that barium sulfate is a salt. And now we have to find the source for barium. So it can be either barium metal, it can be barium hydroxide, the base, or it can be barium carbonate. Yeah, barium carbonate. For sulfate, well, only one source, so sulfuric acid. So sulfuric acid here. So you can choose actually any of these three. So one of these three is okay. Yeah, any of these three is okay. But maybe barium is not a good example. Yeah, but it's okay. So you can choose any of these three sources of barium and sulfuric acid, and then you can have your barium sulfate. But what would be the method? So first, let's say that I choose the base here and the acid. Let's say, just for preference. So let's say that I prepare barium hydroxide, yeah, and then sulfuric acid. I prepare them. So the next step is that I pour one of them to the other. So I mix them. So it means that here in this bigger glass, I have a mixture of them. Because they are mixed, actually, they will form the salt. Because they already react, right? Barium hydroxide plus sulfuric acid will form barium sulfate and water. But barium sulfate is actually insoluble. Therefore, once you react, the barium sulfate will accumulate at the bottom of the bigger glass. So what you need to do to remove this is that you need to filter. So let's say that you do this. So you filter using a filter paper to another container, and then later your barium sulfate will be on your filter paper, and then the liquid will still be here. So the thing that is filtered and stuck on the filter paper, we call it as a filtrate. While for the thing that has passed through the filter paper, we call it as residue. You can imagine that the thing that we want is actually this green thing, right? This green thing, the filtrate. Now, since the filtrate is a little bit wet, yeah, we can actually rinse with distilled water, and then we can dry it, yeah, or crystallize it or evaporate it so that it's dry. So the final step is to dry this green thing. So it's very easy to prepare insoluble salt, because technically what you need to do is just mix the two materials. When you mix the two materials, the product will be insoluble, so it's very easy for you to separate. Once you separate, you can treat it, clean it, and dry it. So this method will always work for any insoluble salt. This method is called precipitation because it forms a precipitate. If you want to use barium carbonate and sulfuric acid, it also works. if you want to use barium metal and sulfuric acid, it also works. So you can choose one of these barium sources for precipitation. Technically, usually the acid will be in excess. Sometimes also the acid will be warm, so warm acid. Because if the acid is a bit warm, so the temperature is a bit high, then the reaction will be much quicker, so it's much more efficient for you. Excess, so that whenever you have metal sources, like barium hydroxide, barium carbonate, which might be insoluble, so excess sulfuric acid, make sure that all of the barium actually can be reacted. Okay, now let's discuss the second type of salt. Let's say that I want to make sodium chloride, which is NaCl. Your table salt, very common. So now we have three sources of sodium. We have sodium metal, we have sodium carbonate, and we have sodium hydroxide. For chloride source, well, we only have hydrochloric acid. Okay. So now let's check the solubility chart. That sodium chloride is actually aqueous, or it's soluble, because we check chloride, everything is soluble except for silver and lead chloride, but sodium chloride, so sodium and chloride, soluble. So now it is soluble, and we have the next question, material soluble or not? Now it depends on the material that you choose. Now for example that you choose, yes, the materials are soluble, then we do a titration method. Let's say that I use sodium hydroxide and hydrochloric acid. They will do form sodium chloride and water. Sodium hydroxide is actually aqueous, and hydrochloric acid is also actually aqueous. Because both of the materials are aqueous, we do titration. So how do we do titration from this actually? Now let me show you the steps. So first, of course, you prepare sodium hydroxide and hydrochloric acid. You prepare, and then we will do a titration. So we will put one of them in this instrument called burette. It's with a scale, and then one of them in an Erlenmeyer flask. Usually, it depends on the indicator used actually. The base can be here and the acid can be here, or it can be the other way around. So the acid can be here or the base can be here, but it's okay. Both of them works. So you know that this is called burette. It has a valve, and the valve actually can be opened so that the solution can drip down and react with whatever it is in the Erlenmeyer flask. In order to move one of these two solutions to the burette, usually you use a pipette, right? But a pipette will take so much time, so we use what is called a volumetric pipette instead. A volumetric pipette. Like this. It's called volumetric pipette. You move, and then you pour here, also to the flask. You fill. So now imagine that this is sodium hydroxide and this is hydrochloric acid. Imagine. So initially, the pH of the solution in the flask will be very low pH, because it is filled with hydrochloric acid. But then as time goes by, and then you pour little by little sodium hydroxide, the pH inside the Erlenmeyer flask will actually increase. Slowly but slowly it will increase until at one point it will be completely neutral. But the question is, when do we know that the reaction has actually achieved that point That is why usually we put what is called by indicator. So indicator are actually chemical compounds that change color depending on the condition of your solution. So there are indicators that can change color from, let's say, acid to neutral or acid to base. Therefore, what you need to do is that first fill the burette with the base, let's say sodium hydroxide. And second, take some hydrochloric acid with volumetric pipette and put it inside an Erlenmeyer flask or a flask. Don't forget also to put indicator to the hydrochloric acid solution. And then titrate. Or open the valve doing titration so that the base can actually react with hydrochloric acid. And do this until the solution changes color. Yeah, maybe it's here. So then you know the volume exactly how many milli of sodium hydroxide will completely neutralize hydrochloric acid. So in this case, you can record the volume to completely neutralize. Now, you can do it one more time in order to create the salt that you want. But this time, since you already know the volume, now you can do without indicator. So first, like just a preliminary trial, yeah. You try to find the volume of base that can completely neutralize your hydrochloric acid. But why do we want it to be completely neutralized? So let me give you an illustration here. Add water. The base and the acid will react, turn into sodium chloride. So in this case, we only want sodium chloride. We only want this. The thing is that if there are sodium hydroxide remains, yeah, it might disturb our extraction of sodium chloride. Also the same for hydrochloric acid. If it remains, then it might disturb this. So that's why we want these two materials to be completely gone, to be completely neutralized, to completely neutralize each other so that they are both gone. And then we get only NaCl and water. So that's the idea. So after you get only NaCl and water, yeah, they're still in liquid form, right? Then you can actually try them with Bunsen burner. You can do that, yeah. So burn them with Bunsen burner until they are dry. Yeah, they are dry. Something like this. Okay. So the idea is that since the two materials are soluble, you mix them, but you must know the exact solution. You do it by titration. Once you get the solution, then you can do a crystallization here. Evaporation can also work. So this is the second method, if the materials are soluble and soluble. But what if the material is insoluble? So still same sodium chloride, which is aqueous. But let's say, just for curiosity's sake, that I choose sodium metal. Sodium plus hydrochloric acid. So meaning that the sodium is in the solid form while the hydrochloric acid is in the aqueous form. So now we can see how excess solid method works. Because one of the materials actually solid. So what you need to do, so of course first that you have to prepare the materials. Yeah, let's say that this is solid sodium and then this is hydrochloric acid. Now what you need to do is that the insoluble part, the metal part, should be in excess. And then you pour warm acid, so that the reaction will be much quicker. So now imagine, because the sodium is in excess, so after we make it react, we still have some part of sodium, while the remaining of the solution actually already changed into sodium chloride, because the reaction works like that, right? So now what we do, we just pour using a filter paper once more. So here the sodium excess will be on the filter paper, and then the solution will be the residue. Yeah. But now the thing that we want is this. So not the thing on the filter paper. So because the thing that we want is in the liquid form, in order to extract it, we can also burn it using a Bunsen burner. So we heat it. Yeah, we heat until what remains is just the powder form. Okay, so technically there are three methods of making salt, which are titration, precipitation, and excess solid method. And in order to choose one of the method, you should refer to the solubility chart. And then the solubility chart will help you to determine whether something is aqueous or insoluble. So I think this would be most of the things that appear for acid, base, and salt chapter in IGCSE. We speak about the definitions and the scaling, indicators, and also the strength, whether it's strong or weak. We've discussed about oxides and also how to prepare the salt. So I hope this video is useful, and good luck.